Hey, how's it going? So we are going to do the Compton effect examples here. You can see a Compton effect example. It's one example. There's lots of examples here. We're going to talk about what happens as the angle increases. Um, what is the maximum change of wavelength that you can actually have? Because really the only thing that the change depends on is when it hits. Most of them is going to be electron. H and C are both constants, and the angle. Okay, it really has nothing to do with the initial photon is. This could be an sorry, not electron. It could be an X-ray. It could be a microwave. It could be a radio wave. The change will always be the same because it just really depends on when it hits and what angle it scatters at. So the initial type. So I think I might even ask that question. Does it matter what type of EMR it is? It actually doesn't matter. It's just what it hits. Okay? So what's the maximum change? What is the maximum change in the wavelength that an X-ray photon can undergo when you do the Compton scattering effect? So let's think about what it changes, what can change as the X-ray hits um, an electron or something. So it's scattering with electron. So I'm going to draw a few different examples here. I'm going to do quick little calculations. I'm not going to do all of the calculations because we just want to do the one where it gives us the maximum change. What you think of is what would give us the maximum energy difference between the before and after of because the energy is conserved, but of the photon, the energy before and after the photon. What's the change? So let's say we have a photon. Here's my electron. Yeah, it's going to be electrons. So these little dots are going to be electrons. It's going to come along. This is the before. The before is always going to be the same. Okay? Then afterwards, I'm going to have a few different situations here. So afterwards, when I collide with this electron, maybe the electron scatters and goes downwards. Right? And then the photon scatters and goes upwards. Okay? And then I'm just worried about this angle here. Cool. So my wavelength before the scatter is going to be 0.01 nanometers. Not too worried about anything else there. What I'm going to do here is I'm going to think about what happens at different angles. So if my theta was 0 degrees, or if my theta was like 10 degrees, or if my theta was, let's go even bigger, 90 degrees. Maybe I won't do 10 degrees. Let's make this bigger here. What if my theta was like 135 degrees? And what if my 45s? What if it was 180 degrees? Which of these would result in the maximum? Now, you're not going to go past 180 because that would just be the same. It's kind of weird to do. Okay. That would be the same as scattering down, scattering upward, the same. So if I go past 180, so go past 180, that's just the same as going this way, less than 180. So once you go past 180, you just say it scatters the other way. Okay, so let's go through and look at the calculations here for my change in wavelength, which is H over MC 1 minus cos theta. Okay, so this right here is going to be constant. Right? So I want to know what happens when I manipulate the theta, what happens to my wavelength here. Okay, so this stays the same. I don't really care too much about that number. We can calculate that number if you want to. We'll do that later on. What's the momentum of the X-ray afterwards? We'll have to do that. But right now, I just want to deal with this part, 1 minus cos theta, if this side of here is constant. Okay? So I'm just going to deal with this 1 minus cos theta. And we're going to deal with I'm going to put in 0, 45, 90, 135, and 180. And I'm going to see what happens. Okay? So I'm just worried about this piece. So when I have 0 degrees, 1 minus cos 0 degrees, what happens, if you know anything about unit circles and stuff, cos is the x value. When is cos equal to 0? That's 1. So this would be 1 minus 1, which would end up being 0 times a constant, which this will just end up being 0. Okay. So if I don't hit anything, I just go straight on through. There's no angle scatter. Just go straight on through. I'm not gonna transfer energy to anybody else. So I wouldn't have any change. Now 1 minus cos 45. 1 minus cos 45. Cos 45 is like 0.707, I think it is. Yeah, it's 0.707. So it'd be 1 minus 0.707. 1 minus, I'm going to put down root 2 over 2. If you know anything about unit circles, that's what it is. It ends up being 0.293. They put down times. Right? Times whatever that constant, times the constant. Actually, rather than write constant, I'm going to write times h over mc. H over mc. Okay, so this one at least has a value. It's not as big as it could be, but that's fine. It has a value. Now if I do for 90 degrees, cos 90 degrees. Cos 90 degrees is 0. Okay, so a minus is 0. So this ends up being 1 times. Okay, that's promising. It's not a fraction like the other ones or 0 like the other ones. Okay, 1 minus cos 135. Now cos 135 is negative root 2 over 2. So it's a minus. Now don't worry about the root 2 over 2. If you haven't done math 30-1, you want to understand that part, but it's just a number. It's the same thing as 0.707 if you just punch in your calculator. So this will be 1.7, sorry. 1.707 times. Okay, so it's getting bigger, so it's bigger than 1. So I'm multiplying it, gets a little bit larger. Now let's do the last one here. Cos 180. So this one it scatters right back. This one just kind of makes sense that this would be the largest amount because it hits and then it goes straight back. So conservation of momentum says that I have momentum in the positive direction, then it scatters back in the negative direction. If I had positive to start off with, I need positive to start off to end up with as well. So that means I have a little bit of negative. That means the other guy has to be a big positive to balance that out, to make sure I end up with positive. And you'll see that when I do this, 1 minus negative 1 ends up being 2 times h over mc. So the maximum change is when it's going to be a 180 degree scatter. So when it bounces straight back. Okay, cool. Well, that doesn't really answer the question. What is the change? So what my change in my wavelength now is going to be for the maximum amount, because that's what I want. I'm going to do the 180, mc times 2. H over mc, sorry, times 2. The h value, remember to use the h value here, you're going to have to use the 6.63 number. The mass here is whatever you hit. So that's electron. Most of the time it's going to be electron. Some questions like you might see in the assignment, you might say alpha particle, so you just use the mass of an alpha particle there. Okay. Times 2. Okay, so this is not going to be a very big number, but I'm just going to quickly do it in my calculator here. Yes, okay, is that the right number? 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 times 3 times 10 to the 8. Okay, so my maximum change in wavelength is 2.43 times 10 to the negative 12 meters. Okay, so we want to determine the momentum. So we got the wavelength, change in wavelength. We want to determine the momentum of the wavelength before and after here. So we're going to pull out our formula sheet. We're going to pull out the formula for the momentum if we know the wavelength. So the momentum of a photon is h divided by lambda, right? So I want to do this calculation twice, before and after. So the momentum of this wavelength before is pretty easy because they just give us the wavelength up there. So I'm going to use this 6.63 times 10 to the negative 34 joule seconds divided by 0.01 times 10 to the negative 9 meters. So this is going to be before the collision. Okay. Oh, so just 1 second. I lost my calculator. Okay, so I got my calculator here. This is pretty fun because I actually got a calculator on my phone now because I don't have any TI 80. I don't have a TI 84 anymore, so I can use that. So, yeah, so we get 6.63 times 10 to the negative, oh geez, my 10s are really weird, 23 kilogram meters per second. So it's still momentum, so we still have to use those units. It's kind of a strange unit to use, even though we have no mass, right? There's no mass. So why would it be kilograms per second? Well, those are just units. They don't really mean too much other than that's the units for momentum. Okay. So afterwards, to do the afterwards part, we're going to determine what is the wavelength afterwards, so our new wavelength, our final wavelength. Because the change, what I said before, the change is always an increase. So my after momentum is going to be my initial, sorry, wavelength, sorry, it's going to be my initial wavelength plus my change. So it's always going to get bigger. So I'm going to add these two numbers together to get my wavelength. And you're going to notice that there's not going to be too much of a change. You notice also that nowhere else in the calculation above here, just below my head here, nowhere in this calculation down here, did it take into account the wavelength beforehand. All of this just matters what it hits, right? This is always going to be the same change when it hits an electron. So what do we have here? 1.01. I'm going to add on this. Ooh, I should add more sig digs to that, but I've lost my sig digs. And I'm just going to quickly change it back into nanometers to see what it looks like. So my new wavelength is going to be 0.01243 nanometers. So I add those two together. That's what it ends up being. Now what I'm going to do here is I'm going to calculate my new wavelength. This is my after wavelength, or momentum, sorry, by taking my H value and dividing it by this new wavelength that we have here. Okay, so we're going to use that same H value we had before and divide it by that number in meters. Okay. So my new momentum here is going to be 5.33 times 10 to the negative 23 kilogram meters per second. Now, momentum does have is a vector, is a direction, but you notice these formulas here, they don't put the little vector arrows on them. So we can just ignore that for now. You could just say it's going backwards if you want to. There's a direction to the photon. Cool. So let's see what else we have here. Calculate the wavelength of a photon that scatters at an angle of 30 degrees. An X-ray, sorry. Calculate the wavelength after it scatters. Assume it scatters off an electron. Okay, so we're just going to use our delta formula here to find out what the change is going to be if it scatters at 30 degrees. Okay. So let's plug our numbers in there. So we're going to use the 6.63 number still. Joule seconds. We're still going to use the mass of an electron. It says there, assume it scatters off the mass of an electron, but if they don't tell you, just assume it does. That's part of the X-ray scattering that Compton did. He always did it with electrons. Or made the assumption that it hit electrons. And 30 degrees. Okay. Okay, making sure your calculator's in the right mode here. You gotta make sure. Okay. I'm gonna go 6.63. Oops. Divided by bracket. What do we have here? times the speed of light. Awesome. And times, it ends up being the same number as before, that makes sense, times cos 30 degrees, 1 minus cos 30 degrees, ends up being a change in wavelength of 3.25 times 10 to the negative 13 meters. So it changes, but just by a little bit. Now, what I'm going to do with this number is I'm going to divide it by 10 to the power of a negative 9, just to see what that looks like as a nanometer. So still quite a small number. 1, 2, 3, 4. How many is that? 1. So it's going to be 0.000325 nanometers. That's negative 4 there. Okay, so that's how much the wavelength is going to change by. Now remember, change is going to be final minus initial. The change is always a positive number, so my final is going to be the change plus my initial. So this is going to end up being 0.050325 nanometers. Let's put that as 3 sig-digs there. There you go. Looking pretty good. I'm running out of the time here. We're at 16 minutes on this video. I'm trying to figure out, do we just split into the two? Yeah, let's just split into the two. I'll see you in the next video.